প্রিয় শিক্ষার্থীবৃন্দ, আমার সহকর্মী এবং যে সকল দর্শক এই মুহূর্তে ফেসবুক লাইভের মাধ্যমে আমাদের এই ফেসবুক প্রোগ্রামটি দেখছেন, আপনাদের সকলকে আমাদের ফেসবুক পেজ ফিজিক্স আড্ডাতে স্বাগতম। আশা করি সকলে ভালো আছেন এবং সুস্থ আছেন। শুভ বিকাল সবাইকে। আমরা সবাই একটা ক্রান্তিকাল পার করছি। আমাদের সবার জীবনে একটা নতুন অভিজ্ঞতা, ঘরবন্দি জীবন, আমাদের শিক্ষা প্রতিষ্ঠানগুলো বন্ধ। আমরা আমাদের স্বাভাবিক পড়াশোনাটা আমরা চালিয়ে যেতে পারছি না আমাদের শিক্ষা প্রতিষ্ঠানে। আমাদেরকে অনলাইন ভিত্তিক বিভিন্ন শিক্ষা কার্যক্রম চালিয়ে যেতে হচ্ছে। আমাদের ছাত্রছাত্রীদের সাথে আমাদের শিক্ষকদের একটা পড়াশোনার যে একটা মেলবন্ধন সেটা তৈরি করার জন্য আমরা পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয় আমরা চেষ্টা করে যাচ্ছি যে আমাদের ছাত্রছাত্রীরা যেন পড়াশোনার মধ্যে থাকতে পারে। এবং আমরা অনলাইন ক্লাসের পাশাপাশি আপনারা ইতিমধ্যে জেনেছেন যে আমরা বিভিন্ন ধরনের অনলাইন ভিত্তিক প্রোগ্রাম, যার মধ্যে সেমিনার, ওয়েবিনার আছে, আমরা এগুলো চালিয়ে যাচ্ছি। এবং আপনারা জেনে খুশি হবেন যে আমরা যে ওয়েবিনার গুলো করছি সেখানে দেশের এবং দেশের বাইরের অনেক নাম করা পদার্থবিজ্ঞানীরা আসছে এবং আমাদের সাথে তাদের জ্ঞান শেয়ার করছে। এবং ছাত্রছাত্রী এবং যারা এই প্রোগ্রামটি দেখছেন সবাই আসলে উপকৃত হচ্ছে। আপনাদের সবার কাছে আমরা কৃতজ্ঞ, কারণ আজকে আমাদের ওয়েবিনারের যাত্রায় আমাদের 24তম ওয়েবিনার, এবং এটা আসলে সফল হয়েছে আপনাদের সহযোগিতা পাওয়ার জন্য। আপনারা প্রথম থেকেই আমাদেরকে সহযোগিতা করে যাচ্ছেন, যার ফলে আমরা একটা দুটো করতে করতে আজকে আমাদের 24তম ওয়েবিনার। এবং আজকে আমার 24তম ওয়েবিনারে আমরা যাকে পেয়েছি, যে স্যারকে পেয়েছি, আসলে আপনারা তার সাথে কথা বললে এবং তার লেকচার শুনলে আপনারা সবাই উপকৃত হবেন। এবং সে হলো আমাদের সকলের প্রিয়, আমাদের সুরজিৎ চট্টোপাধ্যায় দাদা MIT ইউনিভার্সিটি কলকাতাতে এখন কর্মরত আছে। আপনারা ইতিমধ্যে জেনেছেন যে আমরা আমাদের ওয়েবিনারটি 3টে ভাগে ভাগ করি। আমাদের প্রথমে আপনাদের সাথে আমাদের স্পিকারের একটা পরিচয় করে দেওয়ার চেষ্টা করি, যদিও অনেকেই আমাদের সুরজিৎ দাদাকে চেনেন, তার লেকচার শুনেছেন এবং ক্লাসও করেছেন। তারপরে আমি পরিচয় করে দিব, এবং এরপরে আমাদের একটা সময় থাকবে যেখানে আমাদের সুরজিৎ দা যে তার বক্তব্য, আজকের যে মূল প্রবন্ধ উপস্থাপন করবেন, এবং শেষে আমরা সময় রাখবো লাস্টে 10 থেকে 15 মিনিট বা ডিসকাশনের জন্য। এটা এক্সটেন্ড হতে পারে ডিপেন্ডিং অন দ্য কোশ্চেন। সো আমরা ইতিমধ্যে আমাদের আজকের স্পিকার ডক্টর সুরজিৎ চট্টোপাধ্যায়কে পেয়েছি। আমরা তাকে আমাদের অনুষ্ঠানে স্বাগতম জানাচ্ছি। নমস্কার।
নমস্কার। নমস্কার
আপনাকে আমাদের বিশ্ববিদ্যালয়ে স্বাগতম, এবং আমাদের বাংলাদেশে স্বাগতম, এবং আমাদের ওয়েবিনারে স্বাগতম। এবং আমরা পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়ের পদার্থবিজ্ঞান বিভাগের পক্ষ থেকে আপনাকে ধন্যবাদ জানাই এবং কৃতজ্ঞতা প্রকাশ করছি যে আপনি অনেক ব্যস্ত। আপনাদের অনলাইন ক্লাস এবং অনলাইন ভিত্তিক বিভিন্ন প্রোগ্রাম আপনি করে যাচ্ছেন এই করোনাকালীন সময়ে, তারপরেও আমাদের ডাকে আপনি সাড়া দিয়েছেন। তার জন্য আমরা সত্যিই আপনার প্রতি কৃতজ্ঞ। স্যার, আপনি যদি আমাকে অনুমতি দেন আমি শুরু করতে পারি।
হ্যাঁ, শুরু করুন।
আপনারা ইতিমধ্যে জেনেছেন যে আজকে আমাদের যে ওয়েবিনার, সে ওয়েবিনারের টাইটেল আপনারা ইতিমধ্যে জেনেছেন যে আমরা ইনফ্লেশন নিয়ে কথা বলবো। আজকে আমাদের দাদা আমাদের সামনে কথা বলবে। আমার একটু প্রবলেম হচ্ছে। দাদা কি দেখতে পাচ্ছেন আমাকে?
হ্যাঁ, আপনাকে দেখতে পাচ্ছি। ফিজিক্স আড্ডা পেজটা দেখতে পাচ্ছি।
আচ্ছা, The early inflation and the late time acceleration of the universe, a theoretical overview, আজকে আমাদের যে ওয়েবিনার তার টাইটেল। এবং আজকে আমাদের ওয়েবিনারের যে স্পিকার তিনি হলেন ডক্টর সুরজিৎ চট্টোপাধ্যায় স্যার। উনি এখন ফেলো হিসেবে আছেন রয়্যাল অ্যাস্ট্রোনমিক্যাল সোসাইটি, এবং অ্যাসোসিয়েট প্রফেসর হিসেবে কর্মরত আছেন ডিপার্টমেন্ট অফ ম্যাথমেটিক্স, MIT ইউনিভার্সিটি কলকাতা, ইন্ডিয়াতে। তো আমরা একটু আন্তরিকভাবে দুঃখিত, আমাদের একটু প্রবলেম হচ্ছে, যার ফলে আমি আমাদের আজকে স্পিকার সম্পর্কে ডিটেলস পরে একটু জানিয়ে দেবো আপনাদেরকে। আমার একটু সমস্যা হচ্ছে। আমরা আমাদের স্পিকারের কাছে চলে যাই, আমাদের দাদার কাছে চলে যাই, দাদার বক্তব্য আমরা শুনবো।
তাহলে আমি শুরু করতে পারি?
হ্যাঁ, দাদা শুরু করেন। আমার একটু প্রবলেম হচ্ছে, আমি এটা শর্ট আউট করার চেষ্টা করছি।
হ্যাঁ, বলছি আমার স্লাইডটা দেখা যাচ্ছে তো? আমি কি শুরু করতে পারি? আমি কি শুরু করতে পারি? আচ্ছা, শুভ অপরাহ্ন সকলকে। আমি ডক্টর সুরজিৎ চট্টোপাধ্যায়। আমি কর্মরত আছি ডিপার্টমেন্ট অফ ম্যাথমেটিক্স, এমইটি ইউনিভার্সিটি, কলকাতায়। তো প্রথমেই আমি ডক্টর দাসকে ধন্যবাদ জানাই এই ওয়েবিনারে আমাকে আমন্ত্রণ জানানোর জন্য। এবং এই ধরনের যে ওয়েবিনারগুলো হচ্ছে সারা পৃথিবীতেই হচ্ছে, আমাদের দেশেও হচ্ছে। তো এই ধরনের ওয়েবিনারগুলো একদিকে যেমন শ্রোতা এবং যিনি বক্তব্য রাখছেন তাদের দুজনকেই সমৃদ্ধ করে, অন্যদিকে একটা এই বর্তমানের যে পরিস্থিতি তাতে একটা ইতিবাচক একটা বার্তা দেয় শিক্ষক, গবেষক, অধ্যাপক সকলকেই। তো আমি আমার বক্তব্য শুরু করছি, আমার আলোচনা শুরু করছি। আমার আলোচনার বিষয়, আমার টাইটেলটা দেখা যাচ্ছে যে আর্লি ইনফ্লেশন অ্যান্ড লেট টাইম অ্যাক্সেলারেশন, থিওরিটিক্যাল ওভারভিউ। তো এই বক্তব্যের যে শীর্ষনাম, এর মধ্যেই নিহিত রয়েছে মূল বক্তব্যের মূল নির্যাস। আমরা সকলেই জানি যে আমরা যে ব্রহ্মাণ্ডের মধ্যে রয়েছি, যে মহাবিশ্বের মধ্যে রয়েছি, সেই মহাবিশ্ব ক্রমপ্রসারমান। এবং সেই ক্রমপ্রসারমান মহাবিশ্বের যে প্রসারমানতা তার বিভিন্ন পর্যায়ে আছে, বিভিন্ন পর্যায়কে এই মহাবিশ্ব অতিক্রম করেছে এবং করছে। তার মধ্যে অজস্র বিষয় নিহিত আছে। সমস্ত বিষয়ের মধ্যে যাওয়া তো সম্ভব না একটা আলোচনার মধ্যে। তো সেই জন্য আমি এই আলোচনাটাকে সীমাবদ্ধ রাখছি প্রারম্ভিক পর্যায়ের যে একটা বিপুল প্রসারণ ত্বরণ সহযোগে, সেই প্রসারণ যেটাকে বলা হয় আর্লি ইনফ্লেশন, এবং পরবর্তীকালে যে ত্বরণ সহ যে প্রসারণ যেটাকে বলা হয় লেট টাইম অ্যাক্সেলারেশন। তো এই আর্লি ইনফ্লেশন আর লেট টাইম অ্যাক্সেলারেশন, এই দুটোর মধ্যেই আমার আলোচনাটা সীমাবদ্ধ থাকবে, এবং আলোচনাটা মূলত তাত্ত্বিক, যেটা আমার টাইটেলের মধ্যেই বোঝা যাচ্ছে। তো আমি এবার আমার সরাসরি আমার বক্তব্যের মধ্যে যাচ্ছি। The title of my talk is Early Inflation and Late Time Acceleration, a Theoretical Overview. We are in a universe that started expanding from Big Bang. And this Big Bang is thought to occur 13.7 billion years ago. And the universe is full of mystery. We do not know how long this expansion will go on. The galaxies are receding from Milky Way. The farthest ones are the faster ones as well. And regarding the rate of expansion, there are some issues. For the rate of expansion, the earlier estimation tells that the rate of expansion was 67 kilometer per second per megaparsec. And recently, it has been estimated to be 74 kilometer per second per megaparsec. Now, why this discrepancy? To explain this discrepancy, there are three opinions. One is there might be some unexpected dark energy in the early phase of the expansion. Researchers from Johns Hopkins University have mentioned that has been dubbed as early dark energy. That is one explanation. Another explanation is that the dark matter has a stronger interaction with the visible matters than it is expected to be. There is another explanation. And the third explanation is the presence of dark radiation. That means there might be some subatomic particles that are in combination called the dark radiation that might be responsible for this discrepancy. These are the three explanations to explain that discrepancy. But still, it's a mystery. Our universe is full of such mysteries. And the astrophysics, cosmology, these are all to look at those mysteries, to search for what actually happens. তো এই বিশ্ব চরাচরে, এই মহাবিশ্বে যে যে বিপুল রহস্য রয়েছে, সেই রহস্যের সন্ধানেই অ্যাস্ট্রোফিজিক্স, কসমোলজি সবকিছু। তো এই রহস্যের সঙ্গে, এই রহস্যের পাশাপাশি তো থাকে বিস্ময়। তো বিস্ময়কে যদি আমরা বলতে যাই, তাহলে আমাদের কবিগুরুর কাছে আশ্রয় নিতে হয়। আকাশ ভরা সূর্য তারা, বিশ্ব ভরা প্রাণ, তাহারি মাঝখানে আমি পেয়েছি মোর স্থান, বিস্ময়ে তাই জাগে জাগে আমার গান, আকাশ ভরা সূর্য তারা, বিশ্ব ভরা প্রাণ। কবির এই অমোঘ কয়েকটি পংক্তি, এই পংক্তিগুলি প্রবলভাবে এটাই প্রতিভাত করে যে কি অপার রহস্যের মধ্যে আমরা রয়েছি, কি অপার রহস্য আমাদের বিস্মিত করে, এবং সেই বিস্ময়ের পথেই আমাদের যাত্রা। আমি আমার টেকনিক্যাল পার্টে ফিরে যাচ্ছি। তো বিস্ময় দিয়ে যখন শুরু, তো আমরা একদম অত্যন্ত প্রাচীনকালে ফিরে যাই, in the ancient time. And that time there was no other source of entertainment than looking at the night sky. And astronomy has its beginning at that point of time. Ancient Greek and Indian philosophers believed in geocentric model. What does it mean? Geocentric means the earth was at the center and everything was evolving around that. That was the concept of ancient Greek and Indian philosophers. But that idea of geocentrism was opposed by Nicholas Copernicus in 16th century. And it was proposed by Copernicus that it is heliocentric. That means an astronomical model where the Earth and planets evolve around the sun in the solar system. And in the next century, Johannes Kepler introduced the idea of elliptical orbits. And it was observationally supported by Galileo. And by that time, various improvements started to begin in various aspects. And further observational improvements led to the modern realization that the sun is nothing but one of the hundreds of billions of stars in the Milky Way. And Milky Way is one of the hundreds of billions of galaxies in the universe. And discoveries in the 20th century have suggested that the universe had a beginning and the space has been increasing since then. And currently, what you know is that the universe is expanding with acceleration. This is in a nutshell, the evolution of ideas regarding the universe. Now, this is the summary of what I'm going to deliver for the next 1 hour. Firstly, I'll have to discuss the evolution of history, the evolution of the universe, the evolution history of the universe. Then I will give an overview of the late time acceleration. Then I will give an overview of inflation, although inflation occurred earlier. But after this overview of late time acceleration, I'll go back to inflation. But during this time, these are correlated. The talk is correlated. Sometimes while discussing the lit time acceleration, I may have to talk a few things about the inflation. And finally, I'll report some research works on lit time acceleration and inflation. According to Big Bang theory, our universe emerged from a singularity, a point of infinite density and gravity. And the initial singularity is a gravitational singularity. And as per the prediction of general relativity, it existed before Big Bang and thought to have contained all energy and space-time. The cosmic microwave background, in short, CMB, is evidence that the universe expanded from a very hot, dense state. That CMB, cosmic microwave background, is a very important topic to be discussed in cosmology. I'll give a little bit of discussion on CMB later on. And according to Big Bang theory, I have already mentioned that the age of the universe is 13.799 plus minus 0.021 billion years. That means the Big Bang happened around 13.8 billion years ago. And that is regarded as the age of the universe. Although we think that the universe started from Big Bang, but there are some alternate theories are there to explain the origin of the universe. According to loop quantum gravity, there might have been a series of bounces that led to the origin of the universe, and the quantum fluctuations are responsible for the expansion. There is another theory that is called the cyclic universe theory. And according to this theory, our universe is a result from the ending up of a previous universe. A previous universe had its evolution ending up to have this universe. This is called the cyclic universe theory. And another suggestion is multiverse theory. According to this multiverse theory, our universe is one of many in a multiverse and has budded off from another universe due to quantum fluctuations. Now let us come to the very important idea of CMB, cosmic microwave background. The CMB is basically a leftover radiation of Big Bang. And it is a strong evidence of Big Bang as well. This CMB, cosmic microwave background, fills the entire universe. And we know that at the beginning, the universe was full of hot plasma that contained particles, mostly proton, neutron, electron, and photon. And that time, at the beginning, it was very dense and hot. Roughly after 3.8 million years from Big Bang, the photons were constantly interacting with free electrons before that. And that is why the photons did not have any free passage. But after roughly 3.8 million years after Big Bang, the electrons started coupling with protons to generate neutral hydrogen. And as a consequence, the intergalactic space became predominantly neutral. It may be stated that due to the gravitational instabilities from the inflationary scenario, the large-scale structures started forming. Now, because of the coupling of electron and proton, the neutral hydrogen started to form. And at the same time, the universe is expanding. And the energy that was contained in a small volume, that has started to be diffused over a huge volume. As a consequence, the temperature is decreasing. And that is why once the electron proton that got coupled, that could not be decoupled, the temperature was too low to make them decoupled. As a consequence, the photons had a free scattering. And due to expansion of the universe, their wavelength got redshifted. And because the redshifting of the wavelength, it got spread over the expanding universe. And as a consequence, the CMB filled the whole universe, and it can be detected only by infrared and radio telescope. The phase when electrons started coupling with protons, that is called the phase of recombination. But later, in a later phase, due to some source of energy, the intergalactic regions that were predominantly neutral by that time started to begin predominantly ionized. But by that time, the universe was heavily diffused. That is why the scattering of photons were not hindered by that. The phase in which that ionization started, that is called the phase of reionization. And as a whole, the phase after the inflation is called the radiation-dominated universe. Now, why this CMB is so important for cosmologists? The CMB carries the imprint of the early universe. Not only that, the complexity of the early universe can be understood through CMB. As I mentioned here, the CMB is useful to the scientists because it helps us to learn how the early universe was formed. This is how CMB formed, and this is why CMB is so important for us. This is the bigger picture. The universe, the beginning, the Big Bang, then inflation. This inflation, that inflation contains the initial condition for structure formation. The initial condition for structure formation lies in the inflationary expansion phase. And that is characterized by large negative pressure. And after inflation, the radiation-dominated phase started. And later, in the energy domination, we have that dark energy. But one common to inflation and dark energy is that both are characterized by large negative pressure. The dark matter speeds up the structure formation, and the dark energy, who is the driving force behind the acceleration, we'll come to this later. The dark energy is the driving force behind the acceleration, late time acceleration of the universe. The dark energy slows down the structure formation, but the dark matter speeds up the structure formation. And after all this is the cosmic web. This contains the stars, the galaxies, the clusters of galaxies, etc., everything, the present. Now, the hot, warm, and cold dark matter, they have very significant influence on the cosmic web because they speeds up the structure formation. So this is the overview of the entire thing. If we look at this pie diagram, it's called the cosmic pie. The first one, the upper one, this is the cosmic pie for today's universe. This cosmic pie shows that approximately 72% of the total content of the universe, total mass of the universe, is due to the dark energy. And dark matter. Why dark? Because they do not interact. Although if interact, then very weakly among itself and others. That is why they are dark. The dark matter and dark energy together, they constitute around 96% of the universe. So 96% of the universe is the dark sector. And rest of the things, the galaxies, anything, those are visible. They constitute only less than 5% of the universe. But this is today's picture. If we look at the lower one, the other cosmic pi, that is 13.7 billion years ago. That means at the time of the Big Bang, after the Big Bang. That time the dark matter constituted 63%, neutrinos 10%, photon 15%, and atoms 12%, but there's no question of dark energy that time. So as in the previous slide, we have uttered the term dark energy. We must say that cosmological constant introduced by Albert Einstein in 1917 is the simplest candidate for dark energy. In 1917, Einstein added the cosmological constant to his field equations to obtain a static universe. Why? How he got the static universe? The cosmological constant is responsible for a repulsive force, and that is counterbalanced by the gravitational attraction. And hence, it is possible to have a static universe. In 1931, Einstein removed the cosmological constant after Friedman introduced cosmic expansion without cosmological constant, and the Friedman's model was matter dominated. In 1967, Zeldovich reintroduced cosmological constant by taking the vacuum fluctuation into account. And in 1998, the breakthrough in modern cosmology, Rees and Perlmutter, they discovered the accelerated expansion of the universe. Why that was a breakthrough? Because up to that, it was believed that the universe is expanding, but with deceleration. And they were working on that, and that time, deceleration parameter was of very much importance. But while working on 34 nearby and 16 distant type 1a supernovae, Rees et al. First discovered the accelerated expansion of the universe. Soon after, almost at the same time, utilizing 18 low redshift and 42 high redshift supernovae, Perlmutter et al. Confirmed the discovery of cosmic acceleration, the breakthrough in modern cosmology, that the universe is expanding with acceleration. And after that, the resurgence of cosmological constant came thereafter. So it's like a wave. In 1917, Einstein added cosmological constant, and in 1931, he removed it. And for 30 years, it was almost of no use. In 60s, Zeldovich reintroduced cosmological constant by taking the vacuum fluctuation into account. And that importance was there for a few years. After that, nothing. And then again in 1998, after discovery of the late time acceleration of the universe, a resurgence of cosmological constant. So the cosmological constant is having a wave-like pattern. Importance, no importance, again importance, no importance, resurgence. So it's very interesting. This is what I have taken from the press release of the Nobel Prize Committee of 2011. Why? Because due to the discovery of late time acceleration of the universe, Saul Perlmutter, Adam Rees, and Brian Schmidt, they obtained the Nobel Prize in Physics in 2011. And what Nobel Committee said, that in 1998, cosmology was shaken at its foundations. Yes, truly the cosmology was shaken at its foundation, because earlier it was believed that the universe is having a decelerated expansion. As two research teams presented their findings, and it may be noted that the two research teams were working independently. Their findings were independent findings, but both of them independently found that the universe is expanding with acceleration. What Nobel Committee said, all in all, the two research teams found over 50 distant supernovae whose light was weaker than expected. That is the proof of accelerated expansion. Distant supernovae, 50 distant supernovae, the light is coming from them, and it is weaker than it is expected to be. This proves that the universe is expanding with acceleration. Otherwise, the light could not have been weaker than expected. This is the picture of Professor Rees, Adam G. Rees. And this is that phenomenal paper of Rees. The title of the paper was Observational Evidence from Supernovae for an Accelerating Universe and a Cosmological Constant. I'm repeatedly emphasizing among these two terms, accelerating universe and cosmological constant. And that work was published in Astronomical Journal in 1998. This paper reported observations of 10 new high redshift type 1a supernovae. What are supernovae? That will come later. 10 new high redshift supernovae type 1a supernovae. And the values of the cosmological parameters were derived from them. This is about Adam G. Rees. And this is a picture of Perlmutter, Saul Perlmutter. And this is their phenomenal paper, measurement of omega and gamma and lambda from 42 high redshift supernovae. Their work was published in Physical Journal in 1999. The reported measurements of the mass density omega m and cosmological constant energy density omega lambda of the universe based on the analysis of 42 type 1a supernovae discovered by the Supernova Cosmology Project. So these are two phenomenal papers that led to the Nobel Prize in Physics in 2011. Now let us come to supernovae. We are repeatedly uttering the term supernovae. What is that? Supernovae. Primarily, supernovae are of two types, type 1 and type 2. Type 1 supernovae are without hydrogen absorption lines in their spectrum, and type 2 supernovae are with hydrogen absorption lines in their spectrum. And type 1 has three subtypes, type 1a, 1b, 1c. But according to some literatures, the basic types are two, type 2 and type 1a. These are the most important types of supernovae. So if these two are the most important types of supernovae, what is their origin? Let us discuss about the origin, how the type 1a supernovae got generated. The type 1a supernovae result from binary star system. In a white dwarf that accretes matter from a companion star. A white dwarf is accreting matter from a companion star. What is the companion star? That you don't know. It is accreting matter from a companion star. Finally, what is happening? This accretion finally leads to an uncontrolled fusion of carbon and oxygen. Finally, the star gets detonated. That is type 1a. And it becomes a luminous object, type 1a. And type 2, these supernovae result from the end of an evolving massive star. That is the end of lifetime of an evolving massive star. When does it happen? Its nuclear fuel gets exhausted and it collapses to become supernovae. These are the reasons behind type 1a and type 2 supernovae generation. So we have discussed about cosmic microwave background. We have discussed about supernovae. So let us come to another important aspect, that is the curved space-time. So let us look at the term space-time. The space-time, this term is very important. To make you understand about the importance of the term space-time, let us now have an overview of how this space-time is associated with the inflationary expansion. Then it will be clear why space-time is so important. The concept of space-time is so important in cosmology and astrophysics. What is the inflationary scenario? Immediately after the Big Bang, the inflationary scenario lasted for 10 to the power minus 36 seconds, unimaginably tiny span of time, 10 to the power minus 36 seconds. And within such an unimaginably small span of time, the universe reached from a very small scale, from a tiny, dense point to cosmological scale. And due to this inflation, in the space-time, along each dimension of space, the universe had a linear expansion of around 10.6 light years. What a huge thing. But in the space-time, no object can have a speed more than light. So then how is it possible? It is because of the space-time geometry. In the space-time geometry, the change in metric is not constrained by the speed of light. It is possible to have this kind of expansion in space-time. That is why this inflation could occur. The property of metric in the space-time. So space-time is very important. The two key concepts of general relativity are what if space-time is curved and what makes space-time curved. When we are in the three-dimensional space, our spatial dimensions are well described by Euclidean geometry, that you know. But when we are in the 3+1 dimension space too, when time is also considered, it has been proven that the geometry of space-time is not flat on cosmological space-time, on cosmological space-time scales. In a very small region, it can be flat, but in the cosmic scale, it cannot be a flat. Therefore, a description of curved space-time is essential in modern cosmology. For two-dimensional curved space, we can intuitively think of embedding it into a three-dimension. It can be done intuitively. However, to investigate our space-time, we cannot intuitively think of higher dimension to embed it into. When we are investigating our space-time, into which will we embed it intuitively? No, it is not possible to have an intuitive way to embed it into a higher dimension. Hence, it is more convenient to use an intrinsic way rather than embedding to describe our space-time. So intrinsic way is more important, is the way out, not the embedding one. So in order to describe our space-time, the intrinsic way requires a description through metric. That metric, the most important term metric that I have already told you, why, how this metric could make inflation possible. The metric tensor is an important quantity in general theory of relativity. It is in fact the geometrical representation of space or space-time. And metric is considered to be the basic block of Einstein's equations of field. It can be calculated from the line element. What is line element? The distance between 2 points in space or space-time. Let us come to Euclidean metric first. To describe that, let us first look at the Gauss assumption. According to Gauss assumption, in any sufficiently small region of the space, we can find a locally Euclidean coordinate system xi1, xi2 in a sufficiently small region of space. Now let us take 2 points at an infinitesimal distance, xi1, xi2, 1 point, and xi1 plus d xi1, xi2 plus d xi2. These are 2 points. What is the separation? The distance can be given by the Pythagorean laws. ds square is equal to d xi1 square plus d xi2 square. Very easy. We can create locally Euclidean coordinate system at any point in an ordinary smooth curved surface by using Cartesian coordinates of a plane tangent to the surface at that point. We consider the surface, there is a point, we create a plane tangent to the surface at that point, and in that plane we can create locally Euclidean coordinate system. By using Cartesian coordinates of a plane tangent to the surface at a given point, we can have that. But can you use this Gauss assumption for any outer properties? No. This assumption is applicable to infinitesimal neighborhoods. So what to do? We consider the xi1, xi2 system, and in that we take 2 points, x1, x2, and x1 plus dx1, x2 plus dx2. The distance ds between these 2 points can be easily calculated as ds square is equal to g11 dx1 square plus twice g12 dx1 dx2 plus g22 dx2 square. This calculation is not at all difficult in general theory of relativity. Everybody does that. Where g11, g12, and g22 are having this form. Very easy to derive that. This form of ds square is the hallmark of a metric space. This form of ds square. And what we face regularly in cosmological problems is ds square is equal to gij dxi dxj. Very well known form. So ds square is very, very important. Let us come to another aspect. In Newtonian gravity, the gravitational potential is determined solely by the density of matter through Poisson equation. Everybody knows this. And here, the gravitational potential is determined solely by density rho. No other thing. But in general theory of relativity, this is replaced by GIK is equal to 8 pi g TIK, the energy momentum tensor TIK. If we consider a homogeneous and isotropic setting, the TIK is the diagonal form to rho minus p minus p minus p. And the Poisson equation hence gets changed to 4 pi g into rho plus 3p. So in the Newtonian setting we had rho, now in the Einstein setting it is rho plus 3p. Thus in Einstein's gravity, the dynamics of space-time is influenced not only by the density of matter but also by the pressure. Now if rho plus 3p is less than 0, the gravity becomes repulsive. Why are you describing all this? Because we are moving towards dark energy. Now let us consider a small mass small m to be under the influence of a very large mass capital M. They are separated by a distance capital R. In Newtonian gravity, the acceleration of the small mass small m would be r double dot is equal to minus g capital M divided by r square, where mass is 4 by 3 pi r cube rho. Rho is the density per unit volume. This m will be attracted and decelerate towards capital M. But in Einstein setting, rho becomes rho plus 3p, and hence this mass capital M also get changed to 4 by 3 pi r cube into rho plus 3p. If rho plus 3p is less than 0, then automatically r double dot is greater than 0, and m would accelerate away from capital M. This is a simple way of understanding the accelerated expansion of the universe. P is a large negative pressure, and rho plus 3p is less than 0 means what? So here, in this context, I need to mention another important cosmological parameter that is called equation of state parameter, that is denoted by W. That is defined as W is equal to P by rho. P is the pressure, rho is the density. So if we divide the left-hand side of this rho plus 3p by rho, then what do we get? 1 plus 3W. Very easy to understand. 1 plus 3W is less than 0. That means W is less than minus 1/3. The W less than minus 1/3 is a necessary condition for the acceleration of the universe. If W is less than minus 1/3, that constant is not satisfied, then the acceleration will not be there. So it's a necessary condition for the acceleration to hold. And that is why for the candidates of dark energy, that constraint must be satisfied, W less than minus 1/3. So there are various candidates of dark energy exist in the literature, but the most simple candidate for dark energy is the cosmological constant lambda. If we look at the equation, Tik is equal to lambda Gik, where Gik is the Kronecker delta, this automatically leads to, if we look at the energy momentum tensor, automatically this leads to P is equal to minus rho. If P is equal to minus rho, this means what? The equation of state parameter P by rho is exactly equal to minus 1. That is one property of cosmological constant. And we have the very famous conservation equation, rho dot plus 3 a dot by a. A is a scale factor or expansion factor of the universe. Rho dot plus 3 a dot by a into rho plus p is equal to 0. It is called the conservation equation. And a dot by a is defined as the Hubble parameter, capital H. So if we look at p is equal to minus rho, then what happens? Rho plus p is equal to 0. Very easy to understand. And finally, the conservation equation gives us what? Rho dot is equal to 0. That means density is constant for cosmological constant lambda. Now, if we take pressureless dark matter, we assume that the dark matter is pressureless. Then what happens? P is 0. Let us look again at the conservation equation. It's a simple ordinary differential equation. It becomes, for P is equal to 0, it becomes rho dot by rho plus 3 a dot by a is equal to 0. And if we integrate, what do we get? Log of rho is equal to minus 3 log of a. Automatically that gives what? Rho is proportional to a to the power minus 3. That means rho is proportional to the minus third power of the scale factor. This is about cosmological constant. So let us come at the Einstein's modified general equation of field equation, where he inserted the cosmological constant lambda. That was done in 1970. And this is the Einstein's field equations without cosmological constant. It is there in any course of general theory of relativity. And here, mu and nu, they vary from 0 to 3. And this leads to 16 equations. R mu nu is the Ricci curvature tensor, and G mu nu is the metric coefficient. And without cosmological constant, this is the form of Einstein's field equation. And one important sentence to be noted here, that is written above the slide: matter tells space-time how to curve, and curved space tells matter how to move. This is a very important and remarkable line for cosmology. We have already told a little bit of historical evolution of cosmological constant, how its importance increased, then decreased, then increased, then decreased, and then increased. Here, a more theoretical description of its evolution. We have already told that in 1917, Einstein proposed the inclusion of lambda to the field equation, and the modified field equation is as what I had shown just one slide before. And another important aspect for Einstein is the Mach's principle. Einstein was very much influenced by the Mach's principle. according to Mach's principle, if there is no matter frame, we cannot have any question of absolute rest or absolute motion. So if our universe encompasses everything, then who will work as a reference frame to describe the motion? An incorporation of Mach's principle made Einstein to postulate a universe that is static and closed on itself, like the surface of a balloon. And static universe could be constructed, as I have already stated. The lambda exerts repulsive force that is counterbalanced by the gravitational contraction. So static universe was possible by the time. But in 1922, Alexander Friedman constructed a matter-dominated expanding universe without cosmological constant. And as a result, what happened? In 1923, in a letter to Will, Einstein quote, had written that if there is no quasi-static world, then away with the cosmological term. And the most conclusive discovery was by Hubble in 1929. And the discovery was of a linear expansion law relating redshift to distance. And this made Friedman models the standard geometrical framework within which Hubble's discoveries were subsequently interpreted. It may be noted that when in 1922 Alexander Friedman constructed a matter-dominated expanding universe, he did not get that much of importance. But after the discovery of Hubble, the Friedman's model became the standard geometrical framework within which the Hubble's discoveries were subsequently interpreted. For detailed discussion on this issue, one can go through the very nice review by Shahanian Starobinsky, published in International Journal of Modern Physics D in 2000. Here we come to another very important question. Our universe is closed or flat? To address this issue, let us look at this picture taken from Perlmutter et al.'s paper that I have already shown you, published in Astrophysical Journal in 1999. Look at this picture. This picture shows that the best fit confidence region in the omega m omega lambda plane favors the closed universe. It is very obvious from this picture. But when combined with the result of CMB, that's very important cosmic microwave background experiments, the combined likelihood of M becomes omega m plus omega lambda approximately equal to 1. From different observational studies, it was believed that the universe is, in the cosmological scale, the universe is flat. But in last year itself, November 2019, there was one work by Valentino et al. Published in Nature Astronomy. There, the Valentino et al. Told that by some statistical analysis that the universe is expanding, but the universe is closed rather than flat. And obviously, that is contrary to lots of studies till date. But that idea has not been supported by Anthony Lewis, who is a cosmologist at the University of Sussex and a member of the Planck team who worked on that analysis. Which analysis? The Planck telescope data analysis in 2018. They scrutinized the outcomes of Valentino et al. And concluded that the idea of closed universe, as obtained by Valentino et al., is just a statistical fluke. It is because of some statistical reasons they got this closed universe. So they abandoned that idea. So hence, for the modeling purpose, the concept of flat universe remains prevalent. Let us come to the other part, the inflation. I have already told some points about the early inflation. This is a very nice picture. This picture is taken from the journal Nature. This gives an overall picture, an inflationary universe. The Big Bang, then inflation. You can clearly see the regions, and then CMB, that blue region, that is the CMB, cosmic microwave background. Then the dark age started. That means the reionization is starting. The clouds of dark hydrogen gas cool and coalescence. Then the stars are forming, galaxies are forming. This is the overall picture, very nice picture to understand the evolution of the universe. Now, regarding the models to understand the early inflation, the models of the early universe that have been constructed before 1979, those were mainly toy models with no definitive understanding of the fundamental physics. Here, this so far means way back to 1970s, not now. Now, importantly, the simple construction do not seem to provide answers to key conceptual questions such as the nature of the cosmological constant and the need to have a unified description of the early universe, which is consistent from the point of view of ultraviolet physics. That unified description is very important. Unified description of early inflation and late time acceleration. Scientists are working on that. Scientists are working. They're trying to see the main problem, the main issue. Who is responsible for this inflationary expansion? After the Big Bang, who is the source of this huge energy? And according to theorists, some scalar field. In fact, some scalar field, a scalar field is known as the inflation. The scalar field is responsible for that. And in recent years, some dark energy fluids are being attempted to examine whether they can get hold of the inflationary epoch. Those studies are going on these days. So unification of early inflation and late time acceleration is a very crucial area of study in the modern cosmology. And here we talk about two very important literatures in inflation. Before the radiation era of the standard Big Bang model, inflation is a postulated period when accelerated expansion of the universe occurred. I have already told you. It was initially proposed as a tentative solution to the problem of the hot Big Bang model. An explanation for homogeneity and flatness is provided by inflation. Let us look at the work by Kleiner in 1966. Although it was not directly a model of inflation, but it can be considered as a precursor work towards inflationary cosmology. Here, Kleiner postulated that there was a phase of exponential expansion before the radiation era. Obviously, in later time, it was found to be the inflationary epoch. So this can be considered as a very important precursor work, the work by Kleiner. And next comes a very, very important work by Alexander Starobinsky in 1979. That was the first semi-realistic model of an inflationary era that was proposed by Starobinsky and published in JETP Letters in 1979. Another model, which is considered to be the first model of inflation by Guth in 1982, that is currently referred to as the old inflation. And in the just next year, Linde proposed another inflation model that is called the new inflation. In 1982 and 1983, two subsequent years had two very important works in the inflationary cosmology, one by Guth, other by Linde, and both were published in Physics PLB in 1982 and 83. So far, we have discussed the theoretical aspects of dark energy, cosmological constant, and inflation. Now I am going to some phenomenological models of dark energy. Although cosmological constant is the simplest candidate of dark energy and is supported by observations and is having a constant equation of state parameter equal to -1, but in the last few decades, many other models of dark energy have been proposed in the literature where the equation of state parameter is time dependent. They can be broadly classified into three classes. One is scalar field models that include quintessence, phantom, and quantum. Second one is Chaplygin gas models. The Chaplygin gas models are not inspired by the field equations. Rather, they are a fluid description of dark energy. It is not motivated by field theory. However, this Chaplygin gas model can work very efficiently as a unification model of dark matter and dark energy. And another important one is holographic dark energy. This holographic dark energy is based on holographic principle. And according to holographic principle, the total entropy of a system scales not with the volume, but with the area of the enveloping horizon. That is the holographic principle. And based on the holographic principle, holographic models of dark energy have been there. I'm coming to that. But scalar field models, those are direct generalizations of cosmological constant. When the scalar field does not roll down, its potential energy behaves like a cosmological constant. And you may go through these very nice reviews on dark energy, very important rather. One by Shahani, published in 2004 as a book, Dark Matter and Dark Energy in the Physics of the Early Universe. And another very important review by Bamba, Capuzziello, Nojiri, and Odintsov, published in Astrophysics and Space Science in 2012. And one historical review, we can say, by Copeland, Sami, and Sujikawa, published in IJMPD in 2006. There are many other reviews are there, but these three are very, very important reviews on dark energy. They deal with so many models of dark energy, beginning from cosmological constant to Chaplygin gas and holographic dark energy models. Next comes, I have already told that Friedman proposed an expanding universe, and this is Friedman's effort, the Friedman-Robertson-Walker metric, that very important metric. Our current universe is considered to be characterized by FRW metric, Friedman-Robertson-Walker metric. And the form of this metric is given here, where r, theta, phi are co-moving spatial coordinates. What does that co-moving means? Co-moving coordinate means it is a coordinate that expands in the same way as space. That means it is expanding in the same way as the space is expanding. That is called the co-moving coordinate. And we are considering a flat universe. I have already told you, so k is equal to 0. The curvature is 0. And look at the lower panel, the two equations. H square is equal to 8 pi g by 3 rho, where rho is the total energy density of the universe, sum of the matter, radiation, dark energy, everything. This is called the first Friedman equation. And the second equation, E double dot by A is equal to minus 4 pi g by 3 rho plus 3p, where p is the sum of the pressure of each component. These two are called the Friedman's equations, and to model for any dark energy model, we need these Friedman's equations. Now I'll show you a few applications, research applications. Dr. Dash, am I audible? Dr. Dash? Okay, according to the holographic principle, the entropy of a system scales not with its volume, but with its surface area that I told you right now. And when it is applied to the dark energy issue, if we take the whole universe into account, then the vacuum energy related to this holographic principle is viewed as dark energy. And it is usually called holographic dark energy. As I'll show some applications of this, that is why I'm showing this. The holographic dark energy density is given by rho lambda is equal to 3c square mp square L to the power minus 2. This c square is not the speed of light. This c square is a numerical constant. We have maintained this because it was proposed like this, 3c square mp square L to the power minus 2. If we take capital L as the size of the current universe, for example, the Hubble scale h to the power -1, then the dark energy density will be close to the observed data. And these are some very important works on holographic dark energy. And holographic dark energy has many other forms. How does this form come? The holographic dark energy density is proportional to the second negative power of the infrared cutoff. The basic infrared cutoff was 1 by h, and this L has experienced many modifications to have models consistent with observations. These are some forms of holographic dark energy: modified holographic dark energy, holographic rich dark energy, modified holographic rich dark energy, extended holographic rich dark energy, new holographic dark energy, etc. These are some very important candidates of holographic dark energy. And here we are emphasizing upon a very advanced form of dark energy that is called the extended holographic dark energy. This is rho lambda is equal to 3 mp square reduced Planck mass, mp is the reduced Planck mass, into alpha h square plus beta h dot. This alpha beta are constants to be determined. This alpha h square plus beta h dot, this is called the Granda-Oliveros cutoff, and it is the generalization of another cutoff proposed by Nojiri and Odintsov. This is called the extended holographic rich dark energy. Now comes another issue here, although I have no scope to go into details of that, that is called the modified theories of gravity. That is another way of explaining the late time acceleration. It is like the dark energy, but here the left hand side of the field equation gets modified. This is called the modified theory of gravity. That is another way of explaining the late time acceleration. It has many advantages, and to note one important advantage is that in the modified gravity theory, instead of resorting to any particular candidate of dark energy, we can have this accelerated expansion. This is chameleon branch decay cosmology. This chameleon branch decay cosmology is one form of modified theory of gravity. Similarly, there are FR theory of gravity, FT theory of gravity, etc. I am just showing you one application of this. This is my work. This chameleon branch decay, I don't know how much time is left. This chameleon branch decay was proposed by Joseph Biswer in 2012 in a paper published in Physical Review D, PRD. In this chameleon branch decay formalism, the three equations are called the modified field equations. These are called the modified field equations. Here the phi represents the branch decay scalar field, and V phi is the associated potential. Omega indicates the dimensionless branch decay parameter. F phi represents an arbitrary function of scalar field phi. And if phi is equal to 1, we obtain the standard branch decay cosmology. This dot indicates, as usual, the time derivative of the corresponding quantity. We look at the case 1. Case 1, what does it do? Here, potential is assumed to be of this exponential form. The potential, scale factor, not exponential, sorry, power law form, and scale factor is also in the power law form, and F phi and phi, all these are in power law form. And with this power law form, we have this field equation, this modified field equation, and under this modified field equation, we consider these power law forms. And extended holographic dark energy is already mentioned. And from this, we have the reconstructed pressure as P lambda is equal to the right hand side. Look at the third equation. Hence, the modified field equation yields what? the modified field equation yields an expression. And considering the conditions on the coefficients, we have some constraints on omega, m, and n. And these are required for accelerated expansion of the universe. In 1973, omega greater than 5 was consistent with the known data by that time. But by 1981, omega greater than 30 was consistent with the known data. And in 2003, after discovery of the accelerated expansion of the universe, evidence derived from the Cmb Is experiment, this shows that the value of omega must exceed 40,000. Therefore, omega has to be very, very greater than 1 additional constraint. N and m are as obtained. Let us look at the equation of state parameter. I have already told you the equation of state parameter is p by rho. And if equation of state parameter, I forgot to mention over there, if equation of state parameter is greater than -1, then it is called quintessence. If it is less than -1, then it is called phantom. And if it is exactly equal to -1, we get the cosmological constant. So here, look at this plot. We are observing that with passage of cosmic time t, the equation of state parameter is having a transition from above -1 to below -1. That means it's clear indication of the transition from quintessence to phantom. So this model is behaving like quantum. And the deceleration parameter, I have already told you about. It has the formula half plus 3p by 2 rho. The deceleration parameter under this reconstruction is clearly showing a transition from positive to negative. A positive deceleration parameter means deceleration, negative means acceleration. So it clearly gives us the transition from the early decelerated phase to the accelerated phase of the universe. And we go to the case 2. Here we consider scale factor in a0 t to the power n and phi t as phi 0 t to the power n in the second field equation, not in the first modified field equation. We use these answers in the second modified field equation. And based on that, we have reconstructed potential, and also we can clearly get an ordinary differential equation solving which we can easily get the a phi function of the scalar field phi. And this reconstructed potential shows what? It shows an increasing pattern. I'm going very fast because I don't have much time left. These are, and we further see that as phi is tending to 0, f phi is also tending to 0. That means under this reconstruction of extended holographic Ricci dark energy, under the purview of chameleon branch decay cosmology, the reconstruction is satisfying one of the sufficient conditions for a realistic model. And this is the evolution of AF. And from this work, our conclusions were we could get a realistic model and the behavior of equation of state parameter was quantum-like. Next, we're showing the last, this is my last example. The earlier one was my work published in Advances in High Energy Physics. Now, can holographic fluid drive inflation? The modified holographic dark energy, as we have emphasized upon holographic dark energy, I am showing examples from different candidates of holographic dark energy itself. This modified holographic dark energy has this form where the infrared cutoff, the basic problem, what is the basic problem? The basic problem is that we are trying to check whether this holographic fluid can drive inflation or not. I have already told you that some unification is required, something which is, because initially there was, during the inflation, there was accelerated expansion, and in the dark energy phase also there is accelerated expansion. So is it possible to have some candidate that can drive the accelerated expansion in the inflationary as well as in the late time epochs. So keeping that in mind, there is a very important work by Odintsov published in Physics Letters V in very recent time in 2018 or 19. And inspired by that, we tried to see if whether modified holographic dark energy can drive the inflationary expansion. And the infrared cutoff is modified in this inflationary settings, and it is taken to be root over LIR square. That means the infrared cutoff square plus 1 by lambda UV square. This UV is the ultraviolet cutoff. And the conservation equation is as usual, as we have told you. And here we have taken the bulk viscosity. We are trying to see whether any viscous pressure effective in that phase. That is why we have taken effective pressure as the inflationary fluid pressure, thermodynamic pressure, plus the bulk viscous pressure. And based on that, we have the reconstructed Hubble parameter as shown within the purple block. And density of the inflationary fluid is also reconstructed accordingly. And the inflation is started through slow roll parameters, epsilon1, epsilon2, epsilon3. These are called the Hubble slow roll parameters. These slow roll parameters are the key to study inflationary models. We have studied these 3 slow roll parameters, and based on these, we have calculated the spectral indices NS and R that are based on the slow roll parameters. And the 3-dimensional plot shown over here, this shows the evolution of the bulk viscous pressure with evolution of the universe for different cases. And here in equation 9, we have reconstructed the scale factor. And from 9, we can write that the scale factor is approximately the de Sitter solution of scale factor, which is consistent with the basic inflationary feature. And the limiting case, when the ultraviolet cutoff is tending to infinity, the ultraviolet cutoff has a major role in understanding the inflation. Here, we will study the parameters when there is no ultraviolet cutoff. If ultraviolet cutoff tends to infinity, means there is no ultraviolet cutoff. In this case, the scale factor A is calculated in equation 9 as shown over here. And we know that the scale factor and redshift, they are connected this way, A is equal to 1 by 1 plus Z. This implies that Z tends to -1, which further implies that there is a scope for exit from inflation. In this case, the Hubble parameter capital H will take the value root over C1 e to the power -3 alpha. That is not of much importance here. Effective equation of state parameter in this inflationary scenario, when there is no infrared cutoff, is approximately equal to -1, which is consistent with the inflationary expansion. So it is possible. There is a possibility of unifying model that can get hold of the early inflation as well as the late time acceleration. This work has been done by me and my PhD student Cmb Chakraborty, and very recently it has been published in the International Journal of Geometric Methods in Modern Physics. These are the 2 example areas. There are many other areas to explore that we did not have time to discuss. And with that, I end my talk, and thank you all for your patience.
Thank you, sir, for your wonderful presentation. Sir, can you hearing me?
Yes, sir. Yes, Dr. Dash, I can hear you.
Okay, sir. Okay, sorry for the technical problem. I lost my connection. Due to that, I actually cannot answer your question. Maybe in the middle you asked something for me, so I am sorry actually. So, sir, if you allow me, then I can allow our student and the viewer to ask question, and we can start our discussion session.
Yes. Please.
Okay. So we have got some question in inbox, so I can read those if you allow me.
Here I'm seeing one question. In your discussion, you told that scalar field is responsible for inflation. How does inflation be influenced by scalar field? Sir, please explain it briefly.
Yeah.
Actually, according to the literature on inflation, if you go through the literature on inflation, you will see that it is postulated that some scalar field is responsible for this huge expansion. And in some literature, you will find that the scalar field itself is being named as inflation. But in recent times, I just have shown that apart from scalar field, is it possible to have some fluid models that can work as a dark energy model, dark energy candidate for late time acceleration? Can the same fluid be used for explaining the early inflation? That work also is in process. The holographic fluid is the best candidate for that. And I have again told you the scalar field models of dark energy are very much inspired by the field equations. Rather, they are coming from field equations. And the scalar fields, when they are not rolling down, their potential is equivalent to the cosmological constant. And cosmological constant has that repulsive force. It can lead to expansion. And therefore, that scalar field is considered to be responsible for the early inflation in the literature. And in some literature, you'll find that scalar, it's stated that some scalar field is being named as inflation. Any other question?
Yes, sir. Thank you for your answer. So we have another question. So what is the difference between inflation theory and the Big Bang? So one question from the inbox.
What is the difference between inflation theory and Big Bang? No. This is not the question of difference.
Those are
it is the evolution process.
Okay, maybe
this is not the difference.
Okay. Maybe the question is wrong. Okay, then another question. So what is the responsible thing? Why we call the universe is expanding?
Why we are not calling that the universe is expanding? We are not calling that the universe is expanding. The observations and theory, they show that the universe is expanding. Why? Because the observations show that the galaxies are receding from Milky Way. And it is also observed by distant supernova data that the light that is coming from the distant supernova, they are fading out, and that means the universe is expanding with acceleration. So expansion of the universe is an observational proof. We are not saying that. In my lecture, what we are saying that dark energy is a name. We say that this is dark energy, but we don't know what is its exact nature. But expansion of the universe is observational. Yes. Hello, Dr. Das.
আমার মনে হয় এখন মানে কোশ্চেন আর নাই, ডিসকাশন শেষ করতে পারি মনে হয়।
আচ্ছা, তাহলে আমি কি লগ আউট করে যাব?
আপনি লগ আউট করে যান। আমি যদি ট্রাই করছি, কিন্তু আসলে মানে এটা সমস্যাই হয়ে গেল।
আচ্ছা,
করে দেওয়াই ভালো হবে।
ঠিক আছে। আমি তাহলে লগ আউট করে দিচ্ছি।
প্রিয় শিক্ষার্থীবৃন্দ এবং যে সকল দর্শক আমাদের অনুষ্ঠানটা দেখছেন, আপনাদেরকে সকলকে ধন্যবাদ যে ধৈর্য সহকারে আমাদের অনুষ্ঠানটা দেখছেন আপনারা। আমি খুবই দুঃখিত, টেকনিক্যাল প্রবলেমের কারণে আসলে আমাদের ডিসকাশন সেশনটা আমরা সঠিকভাবে কমপ্লিট করতে পারিনি। আশা করি ক্ষমা সুন্দর দৃষ্টিতে দেখবেন এবং আপনাদের সহযোগিতা পেলে আমরা আবার আগামীতে আমাদের কার্যক্রম সঠিকভাবে পরিচালনা করব। ধন্যবাদ সবাইকে, ভালো থাকবেন, সুস্থ থাকবেন এবং স্বাস্থ্যবিধি মেনে চলবেন। ধন্যবাদ।